let's just recall what we did just now. We recalled what is a linear operator, what are its invariant subspaces, and then one-dimensional invariant subspaces are actually eigens. It's through one-dimensional invariant subspaces we defined what is an eigenvector of T. Okay, and then we wrote down this lemma, that is similar matrices have the same eigenvalues because similar matrices represent the same linear operator with respect to different bases. So, if you instead just think of the linear, the eigenvalues or eigenvalues of the linear operator, then this is simple, because this one would just give you a so if x is a coordinate of v, so in particular what we mean here, let's write it down clearly somewhere. And what we are going to do now, from there it will follow that what should we have done for matrices, or let's actually come from that way first and then relate these two logics. Okay, so now the matrix root of the proving the same thing. What is an eigenvector of a matrix? It's AV such that V is not equal to 0 and AV is equal to lambda V, right? Now suppose we are considering some P inverse AP, okay? Multiply it with P inverse V. What do you get? P inverse AV, okay? And V was the original eigenvector. So that would give you just P inverse lambda V, okay? That is lambda P inverse V. Okay? Or do I say eigenvalues? Yes, of course, I have written eigenvalues and not eigenvectors, of course. So if V is an eigenvector of A, then this one is an eigenvector, the corresponding eigenvector of this matrix. Okay? Now let's relate it with what we have just written here, that similar matrices represent the same linear operator with respect to just different bases. Okay? So suppose now that, if we use this notation, then it's a bit problematic now, because now we are going to denote V for the vectors and x for its coordinates. Okay? So once you have written this down, I'm going to wipe this out just not to confuse you with two different notations. Okay? In the meantime, let me clear the other board. So can I clear it up? All right. So now we suppose we take a basis B, a basis of some vector space V. Suppose we have a linear operator T from V to V, and B is a basis, and suppose A is the matrix of T with respect to the basis B. Okay. And consider another, now we are going to consider a similar matrix, a matrix similar to A. Okay. So let A dash defined as P inverse AP be some matrix similar to A. Okay. Now consider the basis B dash defined as BP. Okay. That is, we are taking the linear combination of the elements of B by these columns of the matrix P. Okay. And that is going to give me another basis of B, sorry, another basis of V. Why? Why this is going to be another basis of V? Yeah? Again, Dushyant? P is the change of basis matrix, but still, I mean, why this is going to, so you are getting some n, so suppose n is the dimension, then you are getting n linear combinations of the elements of, I mean, of the basis vectors, right? Why this is going to span V, or why this is going to be linearly independent? What is the logic? P is invertible, wonderful, yes. So if you can go from here to here, you can also come back from here to here by the inverse of the matrix P, okay? All right? So this is a basis of V. Is this point clear to everybody? If not, please let me know, we can explain this again once more. Okay. So we assume it is clear to all of you. Proceed, okay. So B dash is a basis of V, and now the, and what is A dash then? A dash is, now this was the basis, and this one, well, let's just recall, okay? From, if you recall, we had the matrix of a linear operator defined in this manner, and now since it's a linear operator from V to V, and since the only basis we are given is B, instead of this we will just have B here at the beginning, okay? So this is the matrix of the linear operator T with respect to B, okay? And now we are going to see what is the matrix of the linear operator T with respect to this basis B dash. Perhaps you could also already recall that from what you have done earlier, that was Q inverse AP, okay? But Q inverse is here, Q is here P, okay? Let's again recall that. So this is B dash A dash A. Then, I mean, we are going to show that this is indeed A dash. Okay. Let's, okay, so it's, if we are going to show that it is indeed A dash, perhaps we should not write A dash here at first, right? Let it be some matrix M. Okay. And then TB dash is just TB times this one, P, right? But it's a linear operator, so it is compatible with linear combinations. P we can take out then, right? So TBP is equal to BPM, right? Okay, and what more? Now what we are, yeah, right, yeah. So that implies TB is equal to BPM P inverse, right? So PM P inverse, we know that this is equal to, I mean, TB is of course equal to BA as from where we have started, and B is a basis. So every vector has a unique linear combination in terms of B, right? And the columns of each of these are giving linear combinations which are representing some n vectors, okay? So from here, from B PM P inverse equal to BA, we can immediately conclude that PM P inverse is equal to A, okay? That implies PM P inverse is equal to A since B is a basis, okay? And that then implies that M is equal to P inverse AP, that is A dash, okay? So A dash is indeed the matrix of representation of the linear operator T with respect to the new basis B dash, okay? All right. And now we can just apply the logic that, well, at first we are going to say that similar matrices have the same eigenvalues, but we have not spoken anything about the eigenvalue of A yet. Eigenvalues of A yet. So at first, let's see that eigenvalues of A is the same as the eigenvalues of T. Okay. That should be simple. I'm just clearing out this part of the board. There is nothing written here except T. T is a linear operator from V to V. So, well, that was the definition of an eigenvector of T, right, where V is not equal to 0. Now, suppose V is represented by this linear combination X of the basis vectors of V. Okay. Then T of V, that is given by what? Yeah. Yes, of course. T of Bx. Okay, but X is just a linear combination, and so again T is compatible with linear combination, so we can write it that as TBx. Right. Now, what is TBx? Well, TB was BA, so TV is just equal to BAX. Right. Now, TV equal to lambda V, that would mean that this BAX is equal to, okay, can I wipe just this part off? Thank you. Okay. So, TV equal to lambda V, let's write it down now in terms of this notation. Okay. So, TV is then giving you BAX, this is just the left hand part, left hand side, and V was equal to Bx. Okay. So, this is lambda Bx, okay, or you can write this as, okay, P times, I mean the linear combination that you are taking, you can multiply all the elements in that in that array of linear combinations by lambda, and it's the same, right. So, now BAX and B lambda x are these are the same vectors. So, the linear combinations that is giving you, well, not same vectors, it's a single vector. So, the linear combination which is representing that vector is, on the left hand side it is BAX, on the right hand side it is B lambda x, and V is a basis. So, what do we conclude from here? That Ax is equal to lambda x, right. So, that implies Ax is equal to lambda x. Now, that equation defines an eigenvector if, and lambda is an eigenvalue, of course. So, this is an eigenvector and this will be an eigenvalue if x is non-zero. Now, can we say that x is not equal to 0? Why? V is not equal to 0, right. And this is a non-zero vector. It, I mean, if x were 0, then this would just give you a 0 vector, a 0 here. So, that is not the case, and therefore, x is not equal to 0. Hence, we see that every eigenvalue of the linear operator is an eigenvalue of the representing matrix A. Okay, the matrix of representation of T with respect to some basis B. Okay. On the other hand, you can also go back. Suppose you are starting from x equal to lambda x. Okay, that would mean that Bx is equal to B lambda x, right. Now, Bx, suppose Ax is some vector which is, I mean, Ax is giving you V. Okay. So, well, now there is one thing, that is A could be a singular matrix. Okay. So, what happens in that case? So, if, because note that A is just a matrix of a linear transformation, right. A is not necessarily an invertible matrix. Okay. So, what happens if A is a singular matrix? Okay. In that case, we will have, wait a minute, let us write it down somewhere here. Is this board wiped full? Thank you. So, at least what we have obtained from here is that, so till now we proved, till now what we saw is that if lambda is an eigenvalue of T, that implies lambda is an eigenvalue of A. Okay. We are just checking whether there is a 1-1 correspondence, okay, whether we can go back. Okay. And the only thing that will that might hinder us is that if, I mean, here we had x is not equal to 0 because v was not equal to 0. Okay. But if A is a singular matrix, it can happen that x is not equal to 0 and Ax is equal to 0. Is that an obstacle? Let's check. Okay. So now, if A is a singular matrix, then there exists x not equal to 0 such that Ax is equal to 0, right? And we can write this as also as 0 times x. It's a 0 vector. Okay. Now, since x is not equal to 0, v equal to bx is also non-zero, right? Okay. Now, we know that Ax is equal to 0 times x, right? So, if we now write here, so this would give us, wait a minute, here. Now, well, not here, this one, excuse me. This one is giving us Bax equal to b times this, okay, and that is just equal to 0, whereas on this side we are getting Bv, right. Ax was not excuse me, this was not Bv. So this was T of V, right? We just got it somewhere. Yes, T of V is equal to T of Bx, and that is Bax. Okay. So what you are getting is that T of V is 0, and that means it is 0 times V. V is a not equal. V is a non-zero vector. Okay. So the if A is singular, that means 0 is an eigenvalue of A, and that means 0 is also an eigenvalue of T. Okay. Yes. Yeah, Avinash. Yes, 0 is n cross 1 matrix, but once we write x here, this by this notation we are meaning that it's an n cross n matrix. This 0 is now the eigenvalue. Okay. So there's of course a change of notation when we are when we write x equal to 0, that means that this is an n cross 1 matrix. But once we write this one, this means this is a scalar, and this is the n cross 1 matrix. Okay, because we are now going to say that 0 is an eigenvalue of A. But Avinash, thanks a lot for pointing this out. I hope this change of notation was clear to all of you. Okay, this 0 times x is just denoting the 0 matrix, the n cross 1 0 matrix, which is also denoted by this. Okay, and when we are writing this, that at that time we are meaning that 0 is a scalar. Okay, 0 is the 0 eigenvalue of the matrix A. Okay, thank you, Avinash. So is the logic clear to you that if A is singular, then 0 is an eigenvalue of T. In other words, that is if and only if kernel T is not equal to 0. In other words, nullity of T is greater than 1. Do you connect this with some problem that you have seen in the exam? Greater than equal to 1, of course, yes. Yes, thanks. Yeah, it's greater than equal to 1. Now, well, we were just trying to say that if lambda is an eigenvalue of A, whether we can go back. So, if Ax is equal to lambda x, even if A is singular, then this is not causing a problem, because you have consider just the linear combination of the basis vectors with Ax, that is going to anyway give you the linear combination which is given by lambda x, okay? And that you can trace back this to what is Bax, that is T phi, and what is this B lambda x, that is just lambda times V, right? So this is exactly giving you the same equation as this one, okay, in all cases, for all cases, okay. And so you are having this, that is lambda is an eigenvalue of T if and only if lambda is an eigenvalue of A, okay. And note that A was just a representation of T with respect to some basis B, okay. You can choose some other basis, and that will mean that with respect to that other basis, if it is some A dash, again this is having the same eigenvalues as a linear operator T, okay. So similar matrices have the same eigenvalues, okay. Yes. If A is a singular matrix, then, well, if A is a singular matrix, that means the determinant of A is non-zero. Determinant of A is 0, excuse me. And what does it mean? That there exists some x which is not equal to 0, such that you have a non-trivial solution of this. Well, A is non-singular just means that you have a non-trivial solution of this equation with x not equal to 0. Well, what does determinant is equal to 0 means? In the row echelon form, you have an entire 0 column, 0 row, right? Okay, and that 0 row would let you have some non-zero entries in this x, okay, and that would give you a non-trivial solution of this. Here, you note that this is a scalar, as Avinash just pointed out in this notation, okay, and once we have this one, then you can say that 0 is an eigenvalue of A, okay. And since A and well, we just deduce this, right? If 0 is an eigenvalue of A, it should be an eigenvalue of T as well, okay. Okay. Now let's wipe this part out, or yeah, this is the oldest part. This one we can clear out. Okay. So before we move on to something else, just note that if A and A dash are matrix representations of a linear operator T with respect to different bases of V, then have determinant of A is equal to determinant of A dash, right? Because what is A dash? This is determinant of P inverse AP, right? That's what we write, right? P inverse AP, and that would just become determinant of P inverse, determinant of A, and determinant of P, right? So this is just a reciprocal of this one, right? And therefore, you are left with determinant of A. Okay. Okay, we have written the determinant of A. I mean, well, this is just a proof of this thing. Now, what can you say about the trace of? They will be the same. Why? BA. You know this, right? Trace of AB is equal to trace of BA. Yeah. Okay, great. Again, since trace of AB for A and B to say A n cross n, B n cross n, so you don't have any problem multiplying it in this manner or the other manner. You have seen this proof earlier, right? So this one, if not, please do it. Excuse me. What's your name, please? Your name? Ayan. How do you prove this? I saw you were checking your mobile. I thought you were looking at the proof of this. So if you have seen it, please tell. Well, how do you start? It's actually simple. Just think. Just give me the definition. Trace of AB. What is trace of AB? Very good. Yeah. So this is the sum of the diagonal elements, right? So this is you can write AB and then the diagonal elements be I running from 1 to n, say, right? And what are these? How to get this? Okay, for the first element, say this is just okay. Let's write it down somewhere. A is equal to A11 dot dot A1n, A n1 dot dot A_n_n, okay, and B is equal to B11 dot dot B1n, Bn1 dot dot Bnn, okay, and then tell me. Very good. So this is just A12 times B21 plus dot 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 plus A1n Bn1, right? And then the second one would be A21 B12 plus no, what is it? The second one will be just 2 2, right? So A21, yeah, right. So this will go up to A2n Bn2, right? And dot 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 An1 B1n plus dot 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 am I doing things right? Yeah, An1 B1n, yes, of course, to Ann and Bnn. Okay. A11, oh right, yeah, of course. Thanks a lot, Vishesh. Yes. All right, down.
And for BA, we have to do the reverse.
Yes. Okay. But if you, instead of going this way, if you look here, column wise, what do you get? It's just multiplying this one with this one, right? You have B11 times A11, B12 times A21, okay, and so on. So instead of going by the rows, now if you look at the columns, You just get that these are the I mean it's just BA and you are taking the trace again. Okay. So this is equal to summation over BA JJ, say j running from 1 to n, okay, and that is actually giving you the trace on the right side. All right. So now we are going to use this to get that the traces of A and A dash are the same. Okay. So what is A and what is B? Then if we are trying to show this trace of A is equal to trace of A dash, what do you take as your, I mean, you are going to use this, right? So we would like to write trace of A dash is equal to, yeah, now break it in two parts. What is trace of A dash? It is trace of P inverse AP, right? So take this as one part, take this the other part, switch it, and you get trace of, yes, it will be AP P inverse, or yeah, okay, and then you are getting trace of A. This is equal to trace of A. Okay. All right. So we just saw that the determinants of different matrix representations of a linear operator or the trace of different matrix representation of a linear operator remains the same. Okay. And this we may define as the determinant of T. Okay. Determinant of T as the determinant of A, and trace of T as trace of A for some matrix representation A of T with respect to a basis, I mean for a matrix representation with respect to some basis, excuse me, for a matrix A representing T with respect to some basis B of V. Okay. Okay. So we just defined what is the determinant of a linear operator or trace of a linear operator, just as the determinant and or trace of the corresponding matrix with respect to some basis. Okay. Now we saw that similar matrices have the eigenvalues, or well, similar matrices have the determinants, the traces, and the eigenvalues all same. Okay. Now, suppose you have two matrices with the same eigenvalues. Are they similar? What do you think? The question is, are two matrices with the same eigenvalues up to the same multiplicities, it is repeated as often as the other one. So if your matrix have an eigenvalue 2, and so how do you find the eigenvalues of a matrix? By characteristic polynomial. So the number of times it is repeated as a root, that we are just meaning as multiplicities here. Okay. Soon we are going to define two kinds of multiplicities. Yeah. Yes, but here we are just meaning it the number of time it is repeated as a root of the characteristic polynomial. Okay. Up to the same multiplicities. Okay. Right. So are they similar? Yes, Shandip.
Could I say that since they have the same eigenvalues, they have the same characteristic polynomial?
Yes, it has the same characteristic polynomial. So that question becomes now whether two matrices with the same characteristic polynomial are similar.
It's not necessarily true because the actual matrix and its transpose have the same characteristic polynomial.
A matrix and its transpose, yeah, right, sure.
And
Yeah, and why a transpose and a matrix is not similar?
I'm not sure about that one.
Okay, yeah, it's actually a very nice thing to note that a matrix. I mean, so if you take a matrix and its transpose, their characteristic polynomials are the same. Okay, so you may perhaps develop that idea and see where it is leading to. But for this one, you can take some particular examples that would, I mean, say just take some simple 2 cross 2 matrix, okay, and the simplest eigenvalue that you can imagine. Yes, so if you take 1 1 on the diagonal and now put something here or something there, okay, so 1 1 0 1, are these two similar? Why not? Why these two matrices are not similar? It will always be an identity. You can never go from here to there by conjugation. Okay. So these are not similar. Okay, but they have the same eigenvalues. Okay. So now now we come back to the question of Snehamoi, and also somebody else asked this about multiplicities. Shandip asked perhaps about, I mean, you talked about multiplicities, right? So till now, by multiplicities, we were meaning algebraic multiplicities. That is, the number of times it is repeated as a root of the characteristic polynomial. Okay. No, not Sandeep. I think Monideep asked. Okay. Yeah. Okay. Yeah. Okay. So indeed, by multiplicity, I mean, what we meant by multiplicities there, these are called algebraic multiplicities. Okay. Of the eigenvalues. Okay. This is just the number of times it appears, or well, it's a, let's write it down in this form, the number of times it appears as a root of the characteristic polynomial of this matrix A. Okay. That, for example, take this matrix minus 1 1 0 0. Okay, it's a rotation matrix. Okay, it's cos theta minus sin theta cos theta. Okay, what's the angle? Yeah. Again. Pi by 2. Right. You are rotating by pi by 2. It's a rotation matrix. Nothing is fixed except 0. Okay. So there is on R2, this doesn't give any eigenvector. I mean, there is no vector except 0, which is fixed on R2. Right. But if you view this on C, it will have two roots. Right. What is the characteristic polynomial of this? X square plus 1. Okay. So that will have plus or minus I as a root. You see, this plus or minus I only appears if you are considering it over C. not over R. Okay, and over C it makes perfect sense what we have written down here. All right, so now we have to pack up.